Okay, off we go. So we were talking about cross product last time. We're going to pick up with a couple of applications and then a quick notational aside, and then off to the next thing. So y'all may be aware of this idea of torque. This is a very important fundamental concept of mechanics, right? It's kind of like a force, sort of, except forces are thought of as a linear thing. Torque is kind of a rotational version of force, in a sense. And the formula for how to compute torque, you'll notice, involves a cross product. So specifically, what you need to know in order to do that cross product is identify that there's some sort of axis around which you're applying this rotational kind of force kind of thing, right? And when you do that, you're not applying the force to the axis itself, right? You're off the axis. It's like I don't know if you've ever used like a wrench or something, but if the thing that you're turning is like this, you put the wrench and you apply the force some distance away from where the actual axis is. Right? So we're going to call that R, and then there is the actual force. I mean, how you push on the end of the wrench. Well, yeah, that's force, right? And that's a direction and a magnitude in the usual way. So the resulting torque is, again, computed by this cross product. So it comes up naturally in mechanics. This is not a made-up, mathematician fun and games for no apparent reason kind of a situation. It is physically natural. And here's another example of how it comes up in the real physical world, and that is magnetic fields. So magnetic fields are kind of weird things. Some of y'all may be taking Physics 152 now or recently or soon. And the reality, by that we notice by experiment, right? This is purely empirical. Don't ask why. Nobody knows why. This is just the way it is. If you have a magnetic field pointing in one direction, and if you have a charged particle moving with a velocity in a different direction, then the resulting force, so again, empirically, this is the way it is. Charged particles moving through a magnetic field experience a force, and that force is computed by a cross product. Again, that's the way the world works. So again, very natural, very relevant to real-world considerations. Okay, now this next page is another, for students to read, so there's some details to be aware of here. This is, if I remember correctly, either not in the book or underrepresented in the book, and then there's some questions as to how much you'll see this in engineering classes, how much is it in actual practice, and I can't comment on that. So this thing called the two-dimensional wedge product, it is handy in several places here in Math219. So Professor Aspinwall has written up a very succinct summary of some of the properties of wedge product in this file. That's in the, where did I put that? It's in the course materials folder on the course website. And here's the definition. This wedge product, here it is. The wedge product is defined by that formula right there. Now, a lot of people look at this and think, well, okay, so wedge is determinant. What's the difference? Right? Doesn't it say right there the wedge is the determinant? What are we talking about here? Well, so very importantly, wedge acts on a pair of vectors. Determinant acts on a matrix. Those are not the same thing, right? A pair of vectors is not the same as a matrix. Now, okay, it is true that yes, if you have a pair of vectors, you can choose to assemble them into a matrix in a very natural way. Sure, right, fine. But still, just because they're relatable doesn't mean they're literally the same thing. So we can't say determinant of a list of vectors. It just doesn't really make any sense. Okay. All right, so beware of that distinction. So why should we be interested in this? And, well, roughly speaking, it's a lot like triple product, but just in two dimensions. Remember, the triple product is peculiar to 3 dimensions, right? And then likewise, the wedge product is peculiar to 2 dimensions. And it's also kind of like the cross product in certain ways. So I'm going to let y'all read through those details. It's pretty clear how these connections work and how these likes work. And so be aware, and it's going to show up here and there throughout the course, mostly kind of later in the course, chapter 6, chapter 7, along in there. But anyway, so there it is. Details to be read. I do encourage that you download and read that document as well. Okay. All right, moving along. So I suspect that most of y'all have seen equations of planes previously. And remember, this class has this unfortunate feature that we have so much material to cover, and any time I spend now is pulling time away from vector calculus chapter 6 and 7 and stuff that really is going to have stronger case for deserving time spent in class. So I'm going to move somewhat quickly through this, but the big idea is if you have a plane. Now you got to tell me which plane you're talking about, and I claim that what we call a normal vector and a starting point, different names you could give them. If you give me a point in the plane and a vector perpendicular to the plane, that characterizes the plane, right? If I say I'm thinking of a plane, well, that's kind of vague. There's a lot of planes. But if I say my plane goes through that point and is perpendicular to that vector, ambiguity gone, right? There is only one such plane. So the big idea then for how to write down the equation of the plane, keep in mind an equation is a test, right? I need to look at some point R that may or may not be in the plane, and I need a test, a thumbs up or thumbs down. Is it or is it not in the plane? So the big idea of the test is if you want to know if that point's in the plane, is to look at this difference vector, right? And the first observation we make is that difference vector, r minus r naught, well, that's the difference of 2 points in the plane. If we assume r is in the plane, that's a difference of 2 points in the plane, which means that difference is parallel to the plane. And if it's parallel to the plane, geometric appeal, you got to think through the geometry here. If it's parallel to the plane, then it's got to be perpendicular. Let me slow down here. Let's for the moment call it perpendicular. Dot product equals 0 to the normal vector. Right, now again, geometric appeal, parallel to the plane, perpendicular to the normal vector. All right, now let's. I kind of glossed over this perpendicular versus orthogonal thing, right? I mean, I said perpendicular, but then I wrote dot product equals 0, namely orthogonal. What's the difference between perpendicular and orthogonal? Well, it's about the special case of what if one of these vectors is 0. Right? And in particular, we need to worry about the special case of that difference being 0. Right? What if that difference is 0? And, well, if that difference is 0, that means we're testing R being the point R naught, which is given to be in the plane, right? So we want that to be a pass. We want that to count. If we were to say perpendicular, that would exclude R naught from being testing positive as being in the plane, and that's ridiculous. Of course, it should test positive. So, the weird thing about this is that the geometric case that we make to write down this formula in the first place, actually, even though it's the easiest thing to sort of motivate, it's actually not really quite the right test. It's actually orthogonality, not perpendicularity, that we want here. So, anyway, it's just a little subtlety, but you gotta be careful about these sorts of things. So this equation here can be sort of rearranged into this, and I think this is probably the more common form of the equation. Now that said, your normal vector, if your normal vector has coordinates, And of course, our R vector, the vector that we're testing, is xyz. Then notice that green equation turns into this other green equation. So ax plus by plus cz equals d. Kind of cosmetically similar to the equation of a line in 2 dimensions, as it turns out. How about that? Everybody on board? Okay. All right. So by the way, a nice, let me turn this around backwards. Let me say this a little bit differently. If you know the equation of a plane, an awesome convenience is that you can just take these coefficients in the equation of the plane and you can just say, hey, guess what? That is my normal vector. You can just lift those coefficients straight off of the equation. Boom, you know your normal vector. So heads up, that's kind of convenient in a lot of cases. Okay. All righty. Let's see an example. This example is we're going to make use of the equation of the plane that we just talked about. We're also going to see what I like to call the puzzle aspect of a lot of these kinds of questions. A lot of these kinds of questions are, well, you've got various tools, and I'm going to put a task before you. And there is the puzzle of how do I take these tools and kind of combine them together in a way that actually allows me to solve the problem. So you got to know what the tools are and how the tools work, and you also have to be able to solve the puzzle, right? The little strategic, how do I get there from here kind of question. So here we go. We're going to start off with 3 points being given. So there's my 3 points. And the question is to find the equation of the plane, right? And so the equation of the plane, well, it's going to have to be something kind of like this, or I prefer, honestly, this. By the way, let's take a quick aside and compare these 2 equations real quick. We'll go back to the example in a second. Which of these versions do you like better? And it's a pro and con situation. You got to know both for sure. The one on the bottom has the obvious appeal that it's immediately, transparently in terms of coordinates, and isn't that nice? Okay. Here's what I like about the top equation. The top equation is more transparently connected to ideas, right? So what's the deal with this whole ax plus by plus cz thing? Is that just a formula from given to us by the oracle? No. It's a dot product. It's in dot r. That's why the left part of the equation is important. Right? So the top version of the equation is more immediately relatable and connectable to ideas. And again, that's what we do here. Right? That's what the purpose of this course is. Yeah.
Why wouldn't D always be 0 and like ABC is the normal vector? Wouldn't it always, like if it belongs, would it be perfect?
Yeah. So what you got to keep in mind is that this R naught here. This R naught, you can think of it as a point. We're using it as a point here, right? But when it participates in a dot product, it's a position vector for that point, which means it's measured from the origin. And if the origin were here, for example, let's suppose that's the origin, right? Then the position vector for R naught is a vector like that. And when you dot that with your normal vector, purple dot blue here, right? That dot product's not 0. Is that cool? Yeah. Okay, it's a good question. Yes?
If n dot r naught is always 0, why?
It's not. N dot r naught is not always 0. Well, that's what she just asked. No, they're not perpendicular because of the picture I have here. Look at that purple vector. Look at that blue vector. They're not perpendicular. Right? R naught is a point in the plane, but when you want to talk about it as a vector, and as soon as you say perpendicular, you're talking about directions, which means you're talking about a vector, right? It's not a point anymore. Now you have to think of it as a vector. That's the vector. It's not perpendicular. Is that cool? Yeah. Okay. Okay. So, right. So keep in mind we're interested in the equation. Here's our equation, and notice to write that down, I need to know what's my normal vector. And I'm going to need, at some point, to identify some point R naught in the plane that I'm trying to find the equation for. So that's actually the easy part. I have 3 of them. Take your pick. Right? Doesn't matter. We got a bunch of options for what our R naught could be. So the big question is going to be how to figure out what our normal vector is going to be. And now begins the puzzle. I'm given 3 points defining a plane. I want to find a vector perpendicular to the plane. And again, puzzle time, so you got to think strategically. You've got various tools in your toolbox to take advantage of. Good luck. Think craftily. Right? And in this case, here's how you solve the puzzle. The puzzle I would solve by saying, okay, first I'm going to subtract A from B and C, thus giving me 2 vectors parallel to the plane. And then I'm going to notice that if I take the cross product of 2 vectors parallel to the plane, I get a vector perpendicular to those 2 vectors parallel to the plane, and therefore perpendicular to the plane, and therefore I can use that as my normal vector. Right? So now that was clever. How did I know to do that? Well, because I've been playing with these tools in my toolbox for a long time, and I've kind of, I've been shown, by the way, I didn't think this up on my own. Somebody showed me this, right, a long time ago, but somebody showed me this. And so I'm like, oh yeah, okay, that's a cool use of that tool. Made a mental note, and so I'm on the lookout for it. And this particular little trick comes up a lot. Very common scenario. So y'all have tools in your toolbox, and again, you'll need to get some dirt under your fingernails, get some time practicing the use of and the strategizing with these tools by solving little puzzles like this. And you're going to get that on the homework. At least you're going to get some on the homework, and I encourage giving yourself more practice and just by playing around with different things. Okay. Here's a cool observation. I think this is not in the book, if I remember correctly, but maybe it is, but I don't think it is. It's certainly not in a lot of books. And really cool fact, if you have a plane and there are no y's in the equation, right, so the coefficient of y is 0 in your equation, then you can instantly conclude a really cool conclusion, and that is that that plane is parallel to the y-axis. I like this theorem because of how easy it is to notice, right? You don't have to do some computation or deal with sophisticated definitions and conditions to figure out if this blue condition is met. Look at the equation. Either there are or are not y's in that equation. It is super observable at a glance, effortlessly, basically. And at the cost of that very low effort, you get a pretty significant geometric conclusion. Very helpful in a lot of circumstances. So, awesome theorem in that sense. Pretty straightforward to see why this is true. Keep in mind, if you have the equation like so, you can infer the normal vector, right? And it's pretty immediate that normal vector is perpendicular to the y-axis. Easy result from thinking about the dot product, right? The direction vector for the y-axis is 0, 1, 0, and that dot product is obviously 0. And then I make the kind of what I'm going to call a transitivity argument, which is that if we have a plane perpendicular to a normal, and the normal is perpendicular to the line, think about how those dots connect, and it follows, I claim, that the plane is parallel to the line. That's a geometric appeal, by the way. I'm not going to write that down as a theorem. I think it's pretty geometrically satisfying, I hope. It is something you have to kind of ponder. You got to think through the geometry of that, and don't just believe me because I'm saying it, right? But think through the geometry, and I think you can persuade yourself that's pretty believable. Okay. All right. So, neat conclusion. Here's another little puzzle, and suppose I am given a line. Let's see here. All I know about the line is it goes through a given point, and I know that it's parallel to that plane, and it's also parallel to that plane. All right, so here's sort of the picture representing my setup, and the question is, let's try to parameterize that line. Now, keep in mind, if you want to parameterize a line, you need a point on the line. Oh, cool, we already have that. Sweet. And I also then need only to find a vector parallel to the line, right? So that's really my goal at this point, is just to identify this vector parallel to that line. Now again, you got to think. There's a puzzle aspect to this, and you got to think about the geometry and solve the puzzle. What are we given geometrically? Well, I'm given these two planes. I'm given their equations, right? But from that, keep in mind, I can deduce by looking at the coefficients. I can deduce these normal vectors. Right? I can just lift those normal vectors right out of those two equations. Is that cool? Is everybody with me? Okay, and so here we are again. I have certain geometry. I need certain other geometry. What can I conclude from this picture? And, well, it would seem I've got two vectors perpendicular to planes parallel to line. Well, again, this is kind of a connect the dots, knee bones connected to the leg bone kind of thing. And I think it follows that vector V that I'm looking for is perpendicular to N1 and N2. Geometric appeal. So that being the case, of course, I can just take these two vectors and cross them. And that gives me my vector parallel to the line, and the game's over. Solve the puzzle, yeah.
Why doesn't the previous theorem we just saw work for the z-axis? Because now we have...
It does. Oh, yeah, sure, certainly. So you're absolutely, I can at a glance conclude that this is parallel to the z-axis. Right. But the thing is, that's not good enough. Right. So knowing that the z-axis is parallel to that plane doesn't make it parallel to the second plane. In fact, you can see it's not parallel to the second plane. And I'm looking for a line that's parallel to both. Is that cool?
Yes.
Yeah. Okay. Yep.
Didn't it say that L was parallel to both the planes?
Yes.
Then why wouldn't the vector have taken the cross product of N1 and N2? Wouldn't that make it perpendicular?
Nope, makes it perpendicular to both of the n vectors, but its job is not to be parallel to the n vectors. Its job is to be parallel to the planes. The planes are perpendicular to the n vectors.
Got it.
Yeah. Okay, last question. We got to go. Yeah.
How come you can't just set the planes equal to each other, like do x plus y minus 3 equals 0, and set them equal to each other?
So
the line that just lies in both planes.
So I'm not looking for the intersection of the two planes, for one thing. Secondly, if I am looking for the intersection of two planes, I'm looking for points that satisfy both equations, which we realize by creating a system of two equations, not by setting equations equal to each other. In fact, I think if you look back through previous math you've seen, I'll bet you've never seen two equations set equal to each other. And here's, by the way, this is going to come up later in the class as well, but this equation is true, right? And this equation is true. What happens if I set those equations equal to each other? I get garbage nonsense. So that's just not a thing, right? this algebraic act that you described doesn't really correspond to solving a problem. So anyway, something to keep in mind, right? Okay. All right. So we need to move it along. Okay. So these last two examples that I've done, I've made use of transitivities. You know, this is parallel to that, and that's perpendicular to that, and so therefore, right? And sometimes when you're talking about a transitivity, it's a line and another line and a third line. Or sometimes it's a line and a plane and another line. Sometimes it's a plane and a plane and a line. There's various different sort of combinations. And then sometimes it's parallel and parallel, and you want to conclude something. Sometimes it's perpendicular and parallel. There are bazillions of different ways that one could imagine sort of transitivity arguments between these kinds of objects involving these kinds of relationships. I can't write them all down in any practical sense, right? If I did, you would never be able to remember all of them, right? So what I think is the best way to go forward here is to, as I've done here a moment ago, make the geometric appeal, right? So the rule on this in Math219 is you can make geometric arguments. It's fine as long as they're right. Right? So you don't have to memorize a list of which transitivities work and which ones don't. You can cite any one of them that's actually true. So just think through the geometry, think through, wait a minute, can I come up with any counterexample? Is that really true, or am I making up a bunch of nonsense? And here's what you want to watch out for. Here's some nonsense. This vector is parallel to that plane. The plane is parallel to this vector. Does that mean that this vector and this vector are parallel? Nope. Right? So, I mean, now, if on the page, ignoring geometry, ignoring reality, right? Just on the page, it kind of feels like, well, this is parallel to that, that's parallel to the other. Shouldn't that sort of go forward? It doesn't. Easy counterexample. Right? So if you make an argument on an exam or a homework exercise or something like that where you cite a vector being parallel to a plane and that plane being parallel to another vector, and if you conclude that those two vectors must be parallel to each other, that reasoning is invalid. It doesn't work. And I emphasize, you've heard me say it before, you're going to hear me say it a million times coming forward, we're interested in the reasoning, not the result. If it should happen to turn out to be the case in the situation where you attempt to apply this garbage reasoning, if it should happen to turn out that V and W are parallel, doesn't matter. Your reasoning is garbage. Does that make sense? So again, we're interested in the reasoning, right? We're not interested in whether your conclusion is true. So anyway, something to keep in mind. So you got to really, really carefully watch out for garbage reasoning of this sort. Here's another one. P is perpendicular to Q. Q is perpendicular to R. Just looking at the symbols on the page, you might be tempted to suspect that maybe P and R have to have some sort of relationship. Like maybe P and R should have to be perpendicular. Or maybe P and R should have to be parallel. Nope. Neither. No conclusion. This is another one of these situations where there is no sort of transitivity that you can conclude here. So, all right. So moving along. Y'all have seen a construction like this already as a homework exercise. If you have a point and a couple of direction vectors describing a plane, and now again, geometric appeal. If you give me a point, you give me two linearly independent vectors V and W. That characterizes exactly one plane, right? That defines a plane, and we could reasonably ask, what's the equation of that plane, I suppose, but the question we're asking here is, how can I parameterize that plane. And keep in mind that means I want to generate points, right? I want to construct all possible points in that plane. And how do I do that? And the big idea is that, well, if you start at the given point in the plane, you're going to need to kind of go somewhat in the direction of the first vector v, and then followed by somewhat in the direction of the second vector w. In other words, you're going to have to add scalar multiples of those two direction vectors v and w. And if you start in the plane and then you move parallel to the plane, you will remain in the plane. Right? And furthermore, wherever you are in the plane, you can get to by this sort of strategy. So this parameterizes the plane, boom. Okay, so nice little construction. This is called a surface parameterization. Notice that there are two parameters that we need to do this because I'm going to need to know by what multiple of S do I need to move, and also by what multiple, I said that wrong, I'm sorry, by what multiple of V do I need to move, and then also I'm going to need to know by what multiple of W am I going to need to move. So when you have position as a function of two parameters, in some sense you've got kind of 2 degrees of freedom. Generically makes surfaces, not curves. Yeah?
So this is for the statement that you said about, like, if you start in the plane and move parallel to the plane, you'll always stay in the plane.
Yeah.
Is that only generic for, like, infinite planes? Because I remember on the homework, I think the plane was, like, bounded, and so...
Yeah, I hear you.
have to, like, scale it down or something?
Yeah. So I'm gonna have to quibble with your language just a little bit. So the word plane means what you've referred to as infinite plane.
Okay.
Right? So what was in the question was a parallelogram, right? And so a parallelogram is a subset of a plane. This parameterizes the entire plane. In the homework exercise you described, we weren't parameterizing a plane, we were parameterizing a parallelogram, and you do that by restricting the values of S and T. Does that make sense?
Yes, that does.
Okay. Yeah, cool. All right. So here's a quickie example. This is actually an easy one. We've already seen these 3 points. We've already seen the question of understanding the underlying, the plane that contains them. We've already seen that you can subtract and get these direction vectors that are parallel to P. And then when you realize that what we're looking for is a parameterization of the plane, you realize that's all we needed. All we needed were 2 vectors parallel to the plane. Linearly independent vectors parallel to the plane. And then, I guess I also need a point in the plane, so pick your favorite of A, B, C, doesn't matter. Any point in the plane will do. Something kind of satisfying about A, not that it matters. And boom. Okay. Alrighty. So, another detail-heavy category of, real quick, yeah.
I was wondering if there's any way to convert from parameterization to an equation for a plane.
That's right. So, sure. So this is another little puzzle exercise. And so let me I'm going to kind of hit the strategy points here. If you have a parameterization, here, let me erase all of this. If you have a parameterization, then effectively you're given these vectors, right? If you want to find the equation, you're going to need a normal vector. And so the puzzle is how to turn 2 parallel vectors into 1 perpendicular vector, and again, cross product is exactly the tool we need for that. Yeah, sure. Okay. All right. Okay, so detail heavy here. So there's a bunch of there's a category of a bunch of questions, which is how do you find the distance from one geometric thing to another thing? And so, for example, pretty standard example, if you have a point and a line for which you are given a starting point and a direction vector, so maybe you're given a parameterization of the line, how would you compute that distance? Right? So there's the question. And, well, there's different ways you can do this. I'm going to show you 2 different ways to do this. There might be more. I don't know. But anyway, here's the one I'm going to propose. I think this is a nice, clever move, which is that you can subtract to find that vector. You can compute a projection to find that vector. And once you realize that you've got the purple and the blue, then you can observe that that vector is purple minus blue. And then you realize that the distance you're looking for is just the magnitude of that green vector. Right? So that's the little tricky little path that gets you from the givens to the what you need. That's how you solve that particular puzzle. Now think through those details. Make sure you're good with computing projections. Make sure that you don't just follow this little puzzle solution. Make sure you digest and internalize. And I will think to do that in the future. Right? Okay, now here's a different way to do it. Pros and cons. This is really clever, by the way. This is another one that I did not think of, and oh my gosh, this is really clever. Which is why I'm showing you, right? So you don't have to have thought of it. You can capitalize like I've capitalized. Sometimes when you want to compute something, the best way to do it is to compute something else. Something else that involves the thing you're interested in. All right, so I'm interested in this distance, right? And so what I'm going to do is I'm going to compute this area for no apparent reason other than to say that, well, that area clearly involves the thing I'm interested in. So now the first observation I'll make is that area is the distance I'm interested in times the length of the base, right? So this is a high school geometry thing, height times the area, height times the length of the base, right? Again, old news. And then I'm going to compute that area a different way. I'm going to recognize that that area is a cross product, magnitude of a cross product of these 2 vectors. Now that's a different computation of the same area. Okay, we were interested in the green distance. We have now successfully twice computed something we don't care about. So what are we doing? We're just wasting time here, right? So it would seem. But the slick move and why this was a useful idea is to realize that the thing that I'm interested in is involved, and if I compute something 2 different ways, the results have to be equal, and then I can solve for D. This is not just a clever solution. This is an example of a clever category of problem-solving methods. Right? This is a really clever idea of get the thing you care about involved in a computation of something else. So anyway, I think it's really cool in that sense. Now it computes the answer to the same question that we already did up here. Sure, right? But depending on the situation, sometimes this might be more useful. Who knows? Okay, distance between 2 planes is pretty straightforward. 2 parallel planes. If they're parallel, they have a common normal vector. And so I can take any separation, such as that, and I can just ask, well, what is the component of that blue vector in the purple direction? And that component will give me that distance. I got to be careful. Distances are intrinsically positive. Components aren't. The normal vector could have been going the other way. The component could be negative. Right? In which case, I just want the absolute value. Okay, so that's a clever move. This is a really clever one. I did not think of this one either. The big idea here is if you have skew lines, not parallel, not intersecting, just entirely unrelated, no happy coincidences, just no relationship at all, lines. And how do you find the distance? And the beautiful observation is to realize that whenever you have two skew lines, you can always put them into parallel planes, and then the distance between the skew lines is also the distance between those two planes, which we already know how to compute. Right? So it's a really, really clever idea. So how do I persuade you that there are these two planes? Well, all I need in order to have that there are these two planes is that there is a vector that will serve as their common normal vector. And I just need that common normal vector to be perpendicular to both of the lines. If the normal vector is perpendicular to the lines, then I can pick a point on either line, and the line is then in that resulting plane. Right? So how do I find the vector perpendicular to both of the lines? Well, cross product. So it's another really nice little argument. Now again, details, make sure to think it through, but clever, slick move. Okay, let's see how we do it. Oh, we're great. Okay, so let's talk about coordinate systems. Y'all have seen rectangular coordinates many times. So much that you might have even taken them for granted. Right? So we're going to have to not take them for granted. So before I go on and talk about other coordinate systems, I want to recognize some lovely, fantastic features of rectangular coordinates that you might have taken for granted and not really appreciated enough. So here we go. Rectangular coordinates are unique. Seems like a silly thing to say, but if you have a point in the plane, right, there is exactly one set of coordinates to describe where that point is. Well, of course, seemingly obvious. It's not to be taken as obvious. This is a feature of the rectangular coordinate system. And I'm sorry to report, it is not a feature of any of the other coordinate systems we're going to use in this class. So I'm going to have to say goodbye to this seemingly obvious, taken for granted fact. And let's see here. Here's another one. It's just, again, we've done it a million times, that if you have a vector in rectangular coordinates, well, then the coordinates are the coefficients in a linear combination of the standard basis vectors. Right? This is really important fact of linear algebra. Y'all have used this a million times in linear algebra. We'll use it a million more in this class, right? But only for rectangular coordinates. It does not work in other coordinate systems. Nothing like it works in other coordinate systems. And here's a more general statement, arguably, that when you're doing a linear combination of vectors, you see I'm doing a linear combination of vectors here. You can do that by just taking the same linear combinations of the corresponding coordinates. Super handy, right? So handy we've kind of taken it for granted. And again, not true in other coordinate systems. So again, we have to wave goodbye to this convenient tool that we cannot use in any of our other coming coordinate systems. All right, so keep all that in mind, and let's talk about our first new coordinate system here, polar coordinates. Now, again, I think a lot of y'all have probably seen this before. I'm going to give you a slightly different point of view on how to think about it, and maybe possibly correct some misunderstandings. There are various misstatements that get made about polar coordinates and other coordinate systems we're going to talk about. So different ways to think about it. I like to think of the polar coordinates, r and theta, as being the inputs to a function. And there is a function which, if you give me an r and a theta, then I can give you a corresponding x and y in such a way that theta effectively behaves as telling me this angle, measured off the positive part of the x-axis, going counterclockwise, and then the resulting R is how far do I go in that direction. Okay, now I've already committed a little math crime. So let me confess. You'll notice I put how far in quotes. How far suggests a distance. Distance is inherently, unavoidably a positive thing. R does not have to be positive. It absolutely does not have to be positive. R is perfectly allowed to be negative. And if you've got a theta, thus defining a direction, and if somebody gives you a negative value of R, well then you just, I think pretty naturally, go the other direction. Go backwards. So pretty reasonable interpretation and perfectly allowed. Okay, so be aware of this awkwardness. We are going to use negative values of R here and there. That means that when I say R is a distance, I'm lying a little bit. I just don't know a better word, right, to describe, viscerally, geometrically what that R is supposed to be. So forgive my little language crimes related to this point, and on the other hand, you should make sure that you are not suckered in, right, by the sloppiness of the language. Okay. All right, now here's an exercise. Everyone should do this on their own, but given this description and this picture, right, I want you to confirm that the function that does what we've described here geometrically is this right here. In other words, x is r cosine theta, y is r sine theta. You're going to have to make sure you're good with trig. You're going to have to make sure you are comfortable with the unit circle definition of sine and cosine. Forget about that whole triangles business, right? Defining sine and cosine in terms of triangles is very constraining. It only works when you have a triangle. Triangles can only have, the angle can be so big, right? I mean, you can't have a triangle where the angle is 42 pi. Can't do that, right? So sine and cosine are defined more generally. So anyway, good exercise. Make sure you can do that. All right, so a lot of little details that need to be observed, and I'm going to, again, let y'all do most of the observing here. I'm going to just hit a couple of highlights, as I like to do. Addressing the lack of uniqueness. Keep in mind that if you have a point, you can think of that point in relation to a certain angle, defining a certain direction. Right, so in the r theta system, you can think of that direction as being, well, for that value of theta, increasing r takes us in that direction, and you can get to that point. Notice, though, if you were to add pi to your angle, let's just think through what happens if you add pi. Well, pi is a half turn. That, therefore, gets me going in a direction that is what I'm going to call wrong, right? But if you think about it, the fact that it is exactly wrong is actually kind of convenient, right? It has me going in exactly the wrong direction, and so therefore I can just say, well, let's go backwards from the red direction, and sure enough, then that gets me to the point I'm interested in. Right? So this is how you can use a negative r to give an alternative polar coordinate for a given point. Anyway, that's the geometry of it. Now you want to make sure to think that through, and then also think through what happens if you add 2 pi. And keep in mind, of course, 2 pi just means that you're going all the way around and therefore back to, in fact, the exact same direction. Okay, so that's sort of the big idea there. Heads up with your notations. If you write down something like this, right, a lot of people would look at that and say, okay, well, clearly pi over 6, that's clearly an angle, so clearly this is supposed to be r comma theta. Well, It's a good guess. But I mean, technically speaking, pi over 6 is just a real number, right? It's a real number that's commonly used for angles. Yeah. But it's a real number, and y is perfectly allowed to be pi over 6, right? So this pi over 6 could just be your y coordinate. So what you've written here and what I've got circled in blue, it is not clear whether you're talking about this point, interpreting those as polar coordinates, or whether you're talking about this point, interpreting those as being rectangular coordinates. It's not clear from what's written. So heads up, right? Try to be careful about this kind of thing. This mystery is, this ambiguity is easily resolved. All you gotta do is, instead of writing that, just write this, right? You can just, this part right here clearly indicates that you're interpreting these as polar coordinates. Problem solved. Okay, so heads up about that. Next, be aware of some dangers. Now, here's where I think I'm going to be correcting some errors. Like, high schools are typically pretty sloppy about the following, and I get it, right? But we got to make sure that we don't write down garbage. Like, garbage is bad, right? You don't want your bridge to fall down, right? If you're designing a bridge, it's very important that it not fall down. Right, so we've got to get right answers, and therefore we have to be very careful about our reasoning. It's in situations where slightly careless reasoning can give you invalid reasoning. Okay, so here it is. Now you see I've written down this relationship right here, and that's true, and that's fine. But here's what a lot of, I'm just picking on high schools, right? But I've seen this in textbooks, and I've made this mistake myself. It's so easy to inadvertently, out of an urge to sort of finish and solve for R, to write that down, and that is not true. It's not true. That equation that I just crossed out says R must be positive, because that symbol, the square root symbol, that means the positive square root. This is a very common misunderstanding. Again, high schools, maybe I'm just, picking on high schools because of my own high school experience. Anyway, in many contexts, people are kind of loosey-goosey about this kind of thing. And you can't be. That symbol means positive. It does not mean both of the square roots. It does not mean whichever of the two square roots might be convenient in your context. That notation means positive. So that would suggest R has to be positive, and it does not. Okay, likewise, there's a temptation to solve for theta here and write down that theta is arctan of y over x. And that formula, too, is not true. Arctan has a range of allowable values. Negative pi over 2 to pi over 2. That's what that function is. Arctan is always between negative pi over 2 and pi over 2. Theta is not constrained in that way. Right? So you can't just claim like that. It doesn't work. Your bridge will fall down. Is everybody on board? Everybody see what I'm saying? Okay. So I know it's fussy, right? But this is a landmine that we cannot just accept stepping on periodically without realizing it, right? So you just got to be careful about this. So let me show you where you can really get into trouble with this kind of carelessness. If you were to write down what these purple formulas say in regards to this point, -1, -1, right? Well, the square root of x squared plus y squared is square root of 2. The arctan of y over x is pi over 4. And those values produce that point, which is wrong. Right? I mean, there you go. Right? Wrong answer. Everybody see the problem? Okay, so heads up, right? Don't step on this landmine. I didn't plant this landmine. Don't blame me, right? I'm just pointing out where it is, right? So what you have to do instead is use the valid formulas combined with an appropriate consideration of geometry. So these formulas give you these two options for R. I don't know which one. It could be either. It gives you these kind of, I'll say, two options for theta. Again, I don't know which one could be either. I'm not clear, right? And then with those options in mind, think about the geometry of the situation, right? Look at the point you're thinking about and pair them up appropriately. And in fact, in this case, if you pick the positive square root of 2, you've got to choose that value of theta. Or if you choose the negative square root of 2, you've got to choose that value of theta. So do not make the mistake of thinking you can just write down formulas and plug and chug and doesn't work. Exhibit A. Everybody good? Okay. All right, I guess I spent more time on that than I'd intended. This page really is a pretty straight read. A little bit of algebra. You can convert equations from one coordinate system to another. I picked these to talk about first because they're geometrically satisfying. There's another one, another two of them down here. These are both very useful. Make sure to read these. Make sure to have these locked and loaded in your mind. We are going to make regular use of those. This example here, I'm going to go through a little bit of this because this is actually a little confusing, right? If you try to write this equation in rectangular coordinates, it's not going to work out nicely. It just doesn't work well in rectangular coordinates. So what you have to do here is to kind of point plot in a way. And I like to do this more than just one point at a time. I like to think about a range of values of theta. Now do keep in mind theta is the angle measured off of the positive part of the x-axis. So when I say theta between 0 and pi over 2, those are the values of theta we're talking about. So we're thinking about sort of these directions here just to get the ball rolling. Right? And let's think about what the function does for that range of values of theta. And here's the little tricky bit. Notice that if theta is between 0 and pi over 2, the argument of sine goes from 0 to pi. Because of that 2 there, right? And if the thing you're putting in to sine goes from 0 to pi, then sine starts at 0, increases up to 1, and then decreases back to 0. All right, now let's put the pieces together. We're thinking again about this range of values of theta. We have in purple here a picture of kind of what R does correspondingly. R starts at 0, increases to 1, comes back down to 0. And here we go. We start off with 0. As my angle increases, R increases to 1. Notice how my angle is increasing. And R is doing as we've decided that it must do. And then it starts to decrease. And by the time I get up to theta, and keep in mind my thetas are going like this, right? By the time I get up to theta equals pi over 2, I'm back down to 0. And so that traces out this curve that we see right there. And I'm going to leave as a nice related exercise for y'all to think through what happens in the next range of values of theta. So as theta goes from pi over 2 to pi, what happens? And of course, that means that you've got to figure out, well, what's the related range of values of the argument? What does sine do correspondingly? What you're going to find is that sine is negative. And that means that, it's a little bit weird, but as you are looking in these directions, you're going to be going backwards. You'll be going in the negative R direction, and that produces this second petal down here. Second leaf, you might say. Okay, and then I encourage you to kind of keep going and think through the third and the fourth quadrants, if you will, and it turns out this ends up looking like a four-leaf clover. It's kind of fun. So anyway, it's a good exercise to think through, and I encourage you to do so. As always, come to office hours if you have any questions about any of this kind of stuff. And we're going to move it along to cylindrical coordinates. Cylindrical coordinates is a lot like polar coordinates. In fact, it's a kind of a rip-off of polar coordinates when looking at the XY projection in the usual way. And then we just have to recognize that, okay, well, yeah, but we're in 3 dimensions now, and so I just have to say, well, how far do I go up? What is this corresponding value of z? And it's literally the same z from rectangular coordinates. So cylindrical coordinates, very commonly called polar coordinates in 3 dimensions, or polar coordinates in space. Sure, it's pretty much the same thing. Everybody buying it? Everybody okay? All right. So again, a few examples that I think are pretty straight reads. I am going to talk about, well, real quick, let me talk about this one. Here we have a rectangular equation because it involves all the rectangular coordinates, only rectangular coordinates. Here is what we call the cylindrical equation because it involves only cylindrical coordinates. And notice that the way I get from one to the other is by just using that relationship right there. Sometimes sometimes you get lucky, right? And that allows me to turn rectangular into cylindrical. So, kind of cool. Okay. All right, so let's talk about this one, though. This one is a little bit tricky. There's a really nice idea involved with this equation, how I'm going to understand this equation. This idea applies in far more than just this one circumstance. But I'm going to describe it in relation to this one circumstance. And it turns out that there's awesome value in observing that there is a missing coordinate. Right? I see r, I see z. There's no theta. No theta at all. You remember we already saw a theorem where if there's a missing coordinate, right, we stated a theorem that if y is missing out of the equation of a plane, then we conclude instantly something of geometric value, it's parallel to the y-axis. Well, here we are in a different coordinate system. We're going to get a different conclusion, but it remains that there's something pretty cool to observe about that theta is missing. And so here's the observation I'm going to make. Let's think about what theta represents anyway. And roughly speaking, I like to think of theta as representing a plane, I like to think of it as a half plane hinged on the z-axis. So I like to think of the z-axis as being, where the hinges are on kind of a door, if you will. Right? If you've got a door, there are hinges, and then that door kind of rotates around the hinges. Different values of theta would make this half plane just kind of rotate around that z-axis like a door. Metaphor. Okay, all right. So what does that mean about the missing theta? Well, look, theta represents one of these half planes. If theta is missing, that means that the cross-section in any one of these half planes, they all look exactly the same because changing the value of theta doesn't change the equation, not even a little bit, right? If I say, what's the relationship between z and r? For this value of theta, or what's the relationship between z and r for this other value of theta? Same relationship. Z is kr. Right? So in any one of these half planes, right, the relationship between z and r is pretty easy. Z is just a multiple of r. So in all of these half planes, I get the same cross section. Now there is a little awkwardness here. Again, for a given theta, I kind of like to think of a half plane that kind of assumes that r is only positive. It's not. R is allowed to be negative, right? And so when r is negative, then z is negative, And that just kind of continues the line down this other side. So altogether then, the relationship between z and r for any given value of theta is just an angled line like that. And now you can imagine when you rotate that around the z-axis to generate, sort of all of those cross sections, we get this cone that we have pictured there. So it's a really cool argument. The generalization of this is that when there's no thetas, your surface is rotationally symmetric around the z-axis. It's a really cool result. Okay. All right. Let's move it along to spherical coordinates. How are we doing on time? Oh, shoot, we're out of time. Am I seeing that right? No. It's I'm sorry. What time? This ends 11:20. Is that right? Okay, so I've got 10 minutes. Okay, good. Okay. Whew, okay, good. Okay. So spherical coordinates. Another coordinate system. This one, not that much like polar coordinates. It is unfortunately sometimes called polar coordinates in space. That's a mistake. This is a lot less deserving of that term than cylindrical. Cylindrical is a thing, right? So that term, polar coordinates in space, really ought to apply to cylindrical coordinates. Please don't think of this in terms of polar coordinates. Okay. All right. That said, here's the idea of spherical coordinates. We actually are going to start off with frankly, the polar idea of theta. Right? So there's that half plane hinged on the z-axis again. Once we've defined theta, once we've agreed on what theta is, I can then say, from the vertical part of the z-axis, how would I rotate into the theta plane, right, towards that theta half plane, right, and that then defines a direction. Now, very importantly, which way do you rotate off of the positive part of the z-axis? There's a bunch of different directions. There's straight up. I could rotate down that way. I could rotate down that way. I could rotate down that way. A bunch of different options. Which way do you go? Toward the theta half plane. So, again, I like to think of this as you can't really make sense out of phi until you've already decided on your theta. So, something to keep in mind. And then, again, air quotes around the how far, but rho, this Greek letter called rho, pronounced rho, says how far, air quotes, you go in that direction, and once you go that far in that direction, then these are the coordinates of that point. And again, it's not a distance. Rho is a coordinate, not a distance. Rho does not have to be positive. Distances have to be positive. If rho were negative, let me just clean up my mess here. If rho were negative, you just go backwards. You just go that way instead of that way. Reasonable? Okay. All right. So, a little bit of geometry and trig. And I find it convenient to kind of reimagine that triangle. Looking at it straight on, I just find this convenient for my own purposes. You don't have to, but I don't know. Whenever you look at something at an angle, it kind of distorts it a little bit, right? And I just find that intuitively unsatisfying. So anyway, thinking about that triangle, notice that the z-coordinate that I'm looking for in rectangular coordinates, that z-coordinate is pretty easy to write down in terms of rho and phi. Just a little bit of trig, right? And then notice that, for whatever it's worth, r, not that that's one of my coordinates, but while we're here, let me just observe, r is also pretty easy to write down in terms of trig. And once you know what r is, then you can simply recover that x is r cosine theta and y is r sine theta. So that's a quick little hack for how to derive the conversion formulas for spherical, from spherical to rectangular. Just remember that R is rho sine phi. And you remember that, by the way, from the picture. Now, again, for your consideration, everybody's different. Everybody learns in different ways. Yeah, sure. In my life, I have never memorized these equations. I do not trust myself. I know myself well enough that anything that I memorize, I'm gonna forget it. But worse than that is I'm gonna probably misremember it. Right, which is worse, because then you're wrong and don't even realize you're wrong. Right. So my answer to this was, I don't memorize unless I absolutely have to. Right. Anything that I can rederive as needed, I rederive as needed, and this is an easy derivation. If you're comfortable with the sort of geometric trickery here, yeah, it's not like it's hard. Right. And so when I need the formulas for spherical coordinates, I think about this picture in my head. And boom, I write this down. So, again, everybody's different. Y'all do whatever works best for you. At a minimum, you should know these formulas reliably, right? And I think it's healthy, again, to know where they come from. Okay. All right. So let's see here. A little exercise, thinking about spherical coordinates. Let's just go right to the good one. Remember how there were kind of two different ways to write a point in polar coordinates, because theta, you can either have the correct theta or the exactly wrong theta, right? Those are your two different angle options. Well, now we have two different angles, each of which gives you two options, and 2 times 2 is 4. There are 4 different ways, not including the fact that you can always add 2 pi to any angle, right? So important, right? But there are effectively 4 different ways to write a point in spherical coordinates. So real quick, this point here, you can write down the geometry. You can think about the resulting, there's a couple of right triangles here, yada, yada, yada. Y'all are good with geometry and trig. Make sure to do that. And notice, it's pretty easy to argue that that angle is pi over 4. Pretty easy to argue that that angle is pi over 3. And the easy choice of spherical coordinates is to think of theta as being pi over 3, and then to think of phi as being pi over 4. That's kind of the friendly, easy, convenient, satisfying answer, right? But keep in mind, there's a couple different ways to do this. For example, you could have a negative value of phi, right? Negative value of phi, just kind of keep going in that direction until you're going exactly the wrong way, and then choose a negative value of rho, and that'll get you to that same point. It's a healthy exercise to think through those details. What is that value of phi? It's right there in the geometry. You just got to think through the geometry. It's some negative value. And here's another weird way that you could get to that point, and that is to say, let's think about the other possible value of phi. Of theta. Don't think of this as your theta. Go all the way around to where you're going exactly the wrong side, right? And then realize that you could go positive phi with a negative rho. With a negative rho. So a positive phi and a negative rho. Think it through. Make sure to think through what those numbers are, right? Or, arguably easier, you could think of negative pi over 4 as your phi. Keep in mind now, I know that was just what I drew in the picture. That was positive pi over 4 just a minute ago. Why is it negative pi over 4 now? Because remember, phi is always measured positive toward the theta half plane. So once I pick this alternate theta half plane, going that direction is now the wrong direction, right? That phi is negative because it's going backwards from the direction it's supposed to be going. So there we have a negative phi that allows me to pick a positive value of rho. So those are the 4 different ways to think it through. I'm going to leave the trig and the geometry exercise for y'all to think through. And we're out of time. See y'all later. Have a good rest of your Thursday.